Hello, welcome to Rudy's Electronics Lab. And last week I got my new Leo Bodnar 10 MHz GPS disciplined oscillator that I'm going to use as a reference clock in my lab. And tonight the cat is helping me right over here to measure all my devices with internal clock and to see how well they are doing in terms of their accuracy. So let's go and take a look at the results. Okay, here you see an overview of all the devices that I'm going to kind of measure today. And ideally a device would have a very accurate built-in clock. It would also have an output of that clock. It would have an input for a clock that would override the internal clock if you would have something better. And most clocks will be expected to be at 10 megahertz in modern devices. But there's a diversity in devices, the way they work. And in my lab, for example, I got a couple of devices which don't have a 10 but a 30 megahertz clock, for example. And why would that be? Maybe you got some idea. Well, the reason is apparently that 30 megahertz is exactly 48 times the GSM bitrate, and these are GSM telecom testers, and the GSM or the 30 megahertz reference is rather common in such type of installations, and so we also have it in these testers. Some other oddities, for example, will be that in one of my devices there should be a sync out according to specification, but I was just not able to get it working somehow, the routing part. So if anybody knows how to get this working in this REL 6103 device, please do let me know. Yeah, moreover, we ideally a device would have both inputs and output for the clocks, but not all our devices have that. And here you see a bit of an overview. The devices without any node with it, they got an in and an output, but some of them you can see they might have an input in green but not an output, or the other way around, and some devices have neither an input or an output. And we got a couple of devices in which the clock input and or the clock output are somehow shared with another functionality or shared with another on one BNC plug. So you have to select in software what you are using and kind of giving up another function here. Now, I've tried to make a grand overview of all my devices in terms of their exact support of the clock in, clock out, the frequencies of their clock and some more particularities, and particularly also getting into the question if the clock, the internal clock, would be adjustable or not. So first of all, let me turn to the ref clock out column. So you see most of our devices have a clock out, and some of them either can be set to multiple type of frequencies. A couple of them don't have a clock out, and actually what I'm going to do is that I will find other ways to get a signal out of it that can nevertheless allow us to evaluate the device. So typically that will be if the device had like a function generator in it, then I would activate the function generator, ideally at 100 or at 10 megahertz, and analyze that signal. Some of them, like the Picoscope, have a function generator, but it only goes to 1 megahertz, so that will I'll be setting. The spectrum analyzer has a tracking generator that we can set at 10 megahertz. Some other devices like the Fireberd, for example, can have their analysis run at 10 megahertz, so we'll do that. The only thing where we cannot do it at is the Keithley digital multimeter with 6.5 digits. Of course, a bit of an odd device in this list, but I wanted to test it anyway because it can measure frequency. But we'll just measure a known frequency and see what it shows on the display as an alternative. Reference clock in, well, those devices basically we can have an external clock if we need to do some precise work, and especially when there's no internal clock, so the one where the ref clock is in red, then we would really appreciate that the internal clock that we do have to use will be adjustable. And for a couple of devices I know how this is done. So you see that here in green, and there's a variety of ways of doing it. Some older devices you actually turn a potentiometer. Sometimes you can even reach it from the outside of the device. There's some devices where you do it via Skippy. There are devices where you need specific software. There are devices where you can enter an external signal tuning analog signal via a BNC. And actually on one of my favorite devices, the Rohde and Schwarz RTB oscilloscope, it is actually possible via a hidden menu that you have to trigger somehow. Actually, I think I'm going to do a next episode where I'm going to show you exactly how to do that. Now continue a little bit. How accurate can we expect the clock to be? And the clock accuracy generally is the result of the following simplified type of formula. It's the calibration accuracy at the moment that the device was originally or later calibrated. It got an offset for temperature drift because many clocks are sensitive to temperature differences, especially if they are not in an oven, but even ovenized or compensated one might. And then we have an aging rate, which is basically a result of how old the device is, or at least how long ago the last adjustment was, times the aging rate. And many specifications somehow will refer to ideally all these parameters, but they don't always refer to the same parameters. It's hard from standardized, and you get very specific types of claims. One of the instruments, for example, is noting in the spec sheet that the aging is specified after 14 days of uninterrupted operation. Some of them basically also mention the difference between just turning on the device and leaving it up for 24 hours. And one of my devices, as you see it here, it's a CMU, that also talked about a maximum frequency drift with instrument orientation. I don't know what that means actually. I was kind of looking around a little bit. I didn't find it. Anybody that knows it, do post it. What they mean in the spec sheet that you have a increased accuracy if you do instrument orientation, and what that exactly means. Now, looking at it in a more systematic way, here you got it basically what I could find for all my devices in their specification. And as you can see, everybody's kind of reporting it in different ways. So I try to report it as much as possible in the wording or the parameter as was provided by the manufacturer, and that's why we have so many different columns. So for some device we got the one column, for the other device we got the other column there. Aging is sometimes provided as the aging per year, sometimes also the aging per date, but some just provide the accuracy after 1 year and after 10 years, for example. I'm not going to go in great detail looking here at all the devices, but I want to note that it is quite diverse, and the more precise, accurate advices got better oscillators there. This table here also refers to the specific version or options that I got installed in the ones that I got in my lab. So in that case, I'm mentioning it in the second column here. And also do note that some devices like the Keysight oscilloscope or the Picoscope, they do not promise to be any better than 50 ppm. So that is a quite low threshold. Having said that, if you use it for just waveform length measurements, like on an oscilloscope, maybe this is not very critical. Funny enough, if you look at the service manual, I think of the Keysight oscilloscope, to evaluate or to measure its internal reference, it's a rather complicated procedure. In the end, relies, I think, on you observing the length of a wave on the screen. I think they're doing this because it doesn't have a clock out, and not all the versions have a signal generator. I will be using the signal generator to get some signal out related to its internal clock. But if you don't have the signal generator, you have to rely on other types of measures. But anyway, later we're going to see, you know, where the devices actually are, rather than at the specs for accuracy. Yeah, and yeah, so later, right now, we have to go and measure. And basically, I'm going to take my measurement across 3 different roads. And I'm going to tell you in a moment why I do 3 different roads and what are the pros and the cons of each of them. I'm going to use a frequency counter. Actually, it's a signal generator. It's the Siglent 2000X series, which also has a frequency counter in there. I'm going to use an oscilloscope here, and I'm going to tell you in a moment why and how. And I'm also going to use a fairly new device in my lab. It's the tinyPFA, which is a phase and frequency analyzer, which is just made for this type of purposes. So it's exciting to see what it can do. I also considered to do evaluation on the basis of my vector voltmeter. I made a YouTube video about that one. It's a really nice device, but I simply didn't have the time to set it all up and figure all out. But that will be another method basically to be able to do such type of evaluations. Now I want to pay a little bit more attention to each of these types of measuring, because to some degree they overlap, but to some degree they're also complementary, and you can only use the one way of measuring and not the other way of measuring. So let's take a closer look here. Starting with the frequency counter. And this device is not originally designed as a frequency counter, but it got a fairly powerful one in there that can also report like some statistics on the signal, and has a number of settings to kind of shape the input signal. So I think it's pretty nice. So some important observations here is that we are going to measure mostly 10 megahertz clocks. Now, if the clock is just below 10 megahertz, we actually get to see the result in 1/10 of a hertz display. If the value is just above 10, we're going to see it only at 1 hertz, the last digit. So it just sweeps between these two modes. The other thing that I noted basically here is that if you got like a signal which is very close to 10 megahertz, then actually the measurement resolution might not be much better than the actual digit that you're seeing on the screen. Also meaning that the statistics like the mean, etc., might not be the exact value, but might suffer basically from the same inaccuracy as the normal readings as well. And you can see that, for example, here I got I'm measuring a signal here in the big results display, and I know it's not exactly 10 kilohertz, even though it's close to it, but we got reported that it's 0 ppm. Not at all. This is not true, and it might even have to be a 1 here, the last digit, but he's simply not picking it up because I think kind of the measures that he's able to observe don't have enough resolutions to do that. I also saw some cases where you actually got I think plain errors in the deviation when reading really small signals. They were so much larger than they were supposed to be. I think you were just jumping between some bits in the resolution. So we can rely on this. It can measure very big differences up to a certain point, but not very small differences. So altogether, I would say in this device is that the largest difference that you can measure it's really big. It can be even in orders of magnitudes off, no problem at all. The smallest difference I think reasonably will be when the absolute difference will be 1 hertz or so, which basically translate at 10 megahertz to a 0.1 part per million. And I think more accurate than that, this device cannot measure it. There's one nice feature, by the way, here, and I'm showing it right here. You have a reference frequency that you can set, and what it basically means that the deviation in ppm that is shown is relative to this reference here. So if you got some device that has a reference of 30 megahertz, which I do, it can directly show you the right ppm rather than you have to make some calculations to get there. So that's a nice little touch. That's the only thing the reference frequency does as far as I'm aware of. Now, since we also want to be able to measure a little bit more accurate than that, because some of our clocks might be better than the signal is able to pick up, I'm also going to use the oscilloscope. And we do that basically by observing both waveforms, the one of the frequency source that we consider to be a perfect clock, and the one that we want to evaluate. And we simply see these waves moving next to each other if they have a different frequency. And if the time that it takes like to walk just next to each other is exactly 1 second for a full period, that means that we have a deviation of 1 hertz, which is again 0.1 ppm if we're talking about a 10 megahertz source. Now, I'm showing you here a case where we are looking at a rather small difference. So we see the walking process is rather slow. And I think in this particular case, it's about 100 seconds if we get to the full walk over a waveform. So if you're patient enough, you can basically do so. I think in practice, we're going to be a bit limited to observations of say like 100 seconds. So that will be 0.01 hertz in absolute terms, which is 0.001 ppm as accuracy. So we can really measure very small differences accurately using a oscilloscope. We might even do a little bit more precise measurement if we're just patient enough to wait for 1,000 seconds or maybe 10,000 seconds. I might not be patient enough to do that. When the differences are very large, however, you get into trouble because it's simply moving too fast, and I'm going to show it over here, and I don't know how often it walks by per second, and even if it's going to the left or the right, so it doesn't work. I would say, reasonably speaking, a 5 hertz observation, it's about the best that you can do, translating to 0.5 ppm. Now, turning to our next little device in the lab, the tinyPFA. It is a tiny device, tiny in size, tiny in terms of the maximum difference of frequencies it can deal with. I'm coming to that in a second, but also very tiny in price. It's less than 100 euros, and I think it's a quite amazing instrument given the amount of money that it costs. There's actually also a tiny vector network analyzer, which I think is exactly the same hardware, and you can just switch between the two devices basically by just changing the firmware device. I think that's what the manufacturer itself tells. Yeah, very cool device. Do check out tinydevices.org. There's good information on the works of devices from the maker. And let's evaluate again what type of frequency differences we can look at. Now, like I just was saying, it can only evaluate relatively small differences between frequency. It's trying to look for the phase difference, but if the differences are very big, it will not know that actually it's picking up another phase, but don't realize there are multiple other periods of the waveform in between. It simply cannot see that. So what you do is that what you have to do is that you first have to kind of ensure that the difference between the frequencies is small enough for the devices to work with, and then you can proceed. Now you do that by a helping facility in the device. There is a FFT preview, a wide FFT preview that shows you the difference between the waveforms up to plus and minus 37.5 kilohertz. After you have concluded that it's fairly close to each other, you can go to another FFT preview, and there you see the difference between the waveforms within a range of 390 and minus 390. And if you still determine from there they are still very close together, for example like 10 hertz or so, then you can really proceed to the device and do the type of measurement that it is built for. Now, what is the maximum frequency that you can basically deal with? It's for the device defined as 200 hertz divided over tau in seconds, and tau is the measurement time of the device. So if you select tau is 1, then your maximum absolute difference you may measure is 200 hertz, resulting in a difference of 20 ppm for a 20 megahertz signal. And you have to be aware of this. There's nothing wrong with the device. It's a matter of the design, the kind of system design chosen here. But you have to be very aware of what you're doing. I will get back later in the video about more specific advices how to use this device. How about the smallest difference? The manufacturer says that you can measure differences as small as an absolute of 10 microhertz, which actually will be less than 1 parts per billion rather than parts per million. So that's really an order of magnitude higher than anything else. I've been wondering a little bit about that. Can that be true in the first place? Can such a such an affordable device measure things so precisely? So I thought that it might be a nice type of experiment just to feed the device with two identical signals and just see what it is measuring when it's kind of sampling these independently. So this is the little set that I built. I had to use a number of adapters here to make sure I can connect to the ports without mechanical friction. I had to do it rightly, and I used a wrench where I can set the particular force by which I do each of the connections. Nevertheless, these are not particularly high quality type of connectors, so what I'm doing is only kind of indicative here. But at least they are of similar length here, or almost similar length. There's a slight length difference here because the one leg is a little bit longer, I realize. And you also see a terminator. That's another important point. You have to make sure if you're measuring with this device that the input signal is with it a fairly narrow margin of input signal. So you best use an external attenuator to make sure that your signal falls exactly within that spot. So here I got this connected to my absolute reference here, the Leo Bodnar, that I will consider to be perfect, at least in the context of this comparison video with other clock sources which are much more inaccurate. Now let's go and take a look at the results of measuring this. So this is basically what we get if we use it then to analyze our frequency difference and our phase difference. It's very sensitive. Even if you touch your table, give a bang on the table or whatever, you will see everything is already disturbed. You have to leave it really nicely and quietly. So what we're seeing here basically at the right top, we see that the average frequency difference is determined to be as small as 80 nanoseconds. which is less than 0.0, which is 0.008 part per billion at 10 megahertz. So that looks really good. We also see it graphically. We see a scale, that's basically what is shown in the yellow font, of 5 microhertz per division, and we're looking here at the yellow trace, and we see that the yellow trace stays within 4 divisions, so it basically fluctuates somehow between a range of 20 microhertz, which equals 2 parts per billion. And we also see the difference in phase, so DP stands for different phase. You can select all type of different measurements and you can show 4 of them at the same time. I'm just showing only 2 of them, otherwise it's too overwhelming, the screen. But in the blue one here, DP, basically we're seeing the phase difference shown in degrees basically, and it's less than 8 millidegrees. So my conclusion for the time being, that is, yeah, it seems to be very precise. I'm willing to go with the hypothesis that this way we can measure even way more accurately than we can do with the oscilloscope waiting for, say, 100 seconds or so. So yeah, very suitable for very small time differences. Now, this is kind of the overall conclusion in terms of the measurement instruments and when they can be used. We can use the frequency counter basically very well if we want to observe differences up to 1 ppm, maybe 0.1 ppm. Then we're running into accuracy issues. We can in practice use the oscilloscope, I would say, if it's better than 1 ppm, up to 1 part per billion or so. We can even go, I think, 10 times more accurate, but you have to be really patient and wait for thousands of seconds or so for a waveform to repeat itself. And I would say the tiny FPA, it's suitable basically from the difference must be 1 ppm or smaller, but it can all go all the way to, let's say, 10 to the minus 11 or so. Maybe the accuracy is a little bit better on the suggested, as we just saw, maybe to the 10 minus 13. I don't want to go with a claim so far, but I would feel comfortable using it to the point of 10 minus 11 now, which is way better than I'm going to need for the measurements today for my lab instrument. So I think I have a coverage of different measuring instruments that will be allowing me to do the job. Now, I'm not going to talk you through the measurement of each individual instrument. I want to head to the end of the video, but let me quickly show you the measurement of my best internal clock as far as I know in the lab. That will be one in one of my CMU telecom test unit of Rohde and Schwarz. This is unit number 3, and I know that my unit number 3 actually has the best specified oscillator option in it. And also an earlier test, that was the one that was basically coming out the best. So what procedure am I following to measure that instrument with the new tiny phase and frequency analyzer? First of all, I run it on internal batteries, not dependent on anything like a switching power supply. I connect the reference frequency to the one input and the device on the test output to the other input. I'm using attenuators and try to get the input signal somewhere between -10 and -5. Then I think this is reported in the top left of the screen. You will see it here. In my example, it's -6 dB and -5 dBm. So we're nicely within that range. That is the range that the manufacturers advises. It needs to know the frequency, the carrier wave frequency. So we set that to 10 megahertz. It got an internal oscillator. But the manufacturer already says that this is not suitable as a real reference point for very precise measurements. We're using an external source after all. Now, like I explained, we can use this wide FFT and FFT to make sure that the signals are close enough, and you see that on the top right basically. You see here, and actually these signals are so close that we only see one peak here. But if they are deviating from each other, we would see 2 peaks, and we would kind of see how far they are apart. And eventually, with the setting of tau is 1 second, that's the most precise setting that I'm using here, the difference in the end have to be smaller than 20 Hertz to be able to use this device. Then the manual basically tells us, after having been using the FTT mode, turn off the unit. It says that it might not be as accurate if you just return to a regular mode but just restart it altogether. So I did that. Then we set the measurement parameters as we want it to be. We set the measurement time tau, decimation. We set again the carrier wave, which is loss of information. And we can kind of choose the display option. So we can choose how many traces we want to see. We can choose auto scaling or manual scaling on the selected trace. We can do a couple of other things. We're all going to do that here. I'm kind of turning all the traces off because I find it a bit distracting to see a lot of stuff that I actually don't need. And the final results after a bit of testing here is on the right bottom. We see that the clock of the CMU is actually only 6.33 millihertz below the 10 megahertz reference. We're talking about milli and mega here, so it's a 10 to the 12 difference between it. So the difference is minus 0.000633 ppm. So this is very good clock basically, and this measurement result also aligns nicely with the oscilloscope, where I had like a measurement time of 100 seconds, so that also points me kind of in the same direction. It's not exactly the same, but probably our tiny device is able to measure it a little bit better, and I did these measurements on different days as well, so there might be a little bit off, but I'm certainly in the same margin. On the right bottom you also see the green trace, the yellow trace is basically the frequency difference that we are observing. We also get to see a blue type of trace, and that is the phrasing. And I left that in because here you can see that at some point basically it is going through the 180 degrees phase, and then we got this jump again to the other side of the phase diagram. I wanted to leave that in so you see that unless the frequencies are exactly the same, at some point, you know, we're gonna have to go through this phase jump basically to make it work. Yeah. Now we get to the end result. This is the result of all my devices after having been tested, their clock accuracy as it is right now, with their aging, with their temperature difference, whatever, at the moment that I was testing them. And I had to choose a kind of a logarithmic scale because otherwise there was no way to get this well visible. So we see the oscilloscopes are kind of in the range of a ppm type of thing. The Rohde and Schwarz RTB maybe is a little bit less satisfying than I wanted it to be. The Keysight is even a little bit further off. The Siglent and the Picoscope are doing a little bit better. The good news, however, is that the RTB can be adjusted. We got a spectrum analyzer, we got our ARP generators. Funny enough, the ARP generators, the 1000X and the 2000X, I think have similar specifications, but we see that the more expensive device is actually a bit better, quite a bit better in clock. Remind, this is a log scale we're looking at. A couple of more R&S generators. Yeah, quite remarkable, the Rohde and Schwarz AMU 200A, signal generator slash channel equalizer, or channel simulator I should say. It's way off. Yeah, it's over 10 ppm, 15 ppm or so. I don't know what went wrong there, but that device can be changed, can be edited basically. Then we got a telecom test unit, fairly expensive devices. Even though they are very old, we see that they are having very good specs here. The Fireberds are a little bit less precise. We're not surprised, they were not exactly for that type of thing. And I also added in my own do-it-yourself PN9 generator. It just has like a 10 megahertz crystal there. And it kind of behaves as you would expect. It's about 1 ppm, a little bit more, 1.5 ppm. And that is just a crystal with, I think, of €1 or so. This is how good we get if we just have a crystal without basically any type of correction in it. And we got the Keithley DMM, which clearly must just have this €1 crystal as well. So yeah, that brings me, this is kind of all the different results of the lab. I will be taking this further because the one thing that I do want to do is correct some of these devices if possible. And at least the RTB, I found out that it is possible to correct its internal frequency source, which is great because it doesn't have an external input. So I think that's going to be the next episode of my channel. And that's it for now.